Hi, I'm Mads Barnkop and welcome to Kaiser Power Electronics. This is the circuit analysis of the Huawei RRU3928 antenna amplifier or base station amplifier. So let's first take a look at the power supply. So here it is, the power supply in all its glory. It is the bottom half of the whole PCB board that sits in this amplifier unit. There is only one PCB having everything on it. So we can see that over here in the right corner, just behind my head, we have the DC input. Then we have the input choke. There is a full bridge MOSFET inverter here, and it has two output lines, which goes up to the further splitting of voltages and has some planar transformers and a lot of small full bridge MOSFET packages for making the smaller voltages for the CPUs and processors. So let's take a closer look, because there's a few curious details in this design. If we start out here by the DC input connector, my first thought was, hey, that's not soldered in, that's weird. But taking a closer look and trying to pry it out with a screwdriver, I found out that if we look down at this connector over here, we can see there are small holes in the pins. And these are actually spring-loaded, and they are just pressed down into the wire socket in the board. It makes pretty good contact, I would say, because I destroyed the plastic casing trying to pry out the input connector here. A nice big input choke. We can also notice these blue circles here. These are actually spark gaps. So if you have a high enough voltage, these will actually arc over and hopefully absorb a lot of transient energy from maybe switching transients on the net or from lightning strikes. If we go on here, we have a PSMN 4R8 full bridge of MOSFETs. These are rated for 100 volts. I think it was 40 amperes. 100 volt MOSFETs are pretty standard to be used in switch mode power supplies for the telecom industry. Now here we have the two output chokes from the MOSFET full bridge. There's also some additional TVS protection here from for the input. If we go further up, we can see here that we have all these full bridge flat pack they're called the D70N10. And I have not been able to locate a datasheet on these MOSFET packages, but it is clearly either a full bridge or maybe it's just a single MOSFET as it connects with 3 or 4. Yeah, that's probably a half bridge, half bridge, half bridge. And the same over here on the input side. But over here we have some of the high current planar transformers, and we can also see on the voltage rating of the electrolytic capacitors that these are lower voltage switch mode power supplies. As a little peculiar thing, we can see that here it's actually a current sensing resistor, as it is 0.002 ohm. Now let's move on to the next board. Here we have one side of the duplexer. What's worth noticing here is that there is a size difference on the resonators sitting in the cavities. Now here we can quickly tell that the transmitting cavities are the big ones, and that is simply on the observation that there is the most cross-coupling links between these resonators, which makes it the transmit part, as it is most important to shape the output wave of the transmitting part, and the filtering of the received signal is more done by electronics than by the duplexer filter. We can see that the two transmit connectors we have up here, that one goes actually to a resonator, while the other one disappears to the other side of the board. Over here we have the two golden connectors, which are the two receive connectors, and one of these also go through to the other side. So now we are in at full size picture. We can see this has some really nice details, round edges, really smooth machining. It's done in a very fine craftsmanship on this duplexer. If we can take a close look at the lid here, see there's two kinds of adjustment screws. There are some regular flat ones and there's some rounded polished. But overall very fine filter work here. On the other side of the duplexer we have duplexer number 2. And what is really interesting here is it's actually quite different from the other one. Here we can see that it's not symmetrical. The receiving part and the sending and transmitting part has actually been switched around. The placements of the cross couplings in the sending transmitter or the sending duplexer part is not in the same place. The whole design of this duplexer is actually on its own. It's not just a copy of the other one. So that actually leads me to think that maybe this base station amplifier input-output duplexer has the ability to run two different modes, that it's simply not designed for just running two completely same sectors, but it's actually made to run with one of these amplifiers for two different antennas. So it's actually running maybe 3 or 4 different carriers at the same time instead of just multiplexing them. That's quite interesting, and yeah, I can only guess on that. Let's take a closer look at the transmit part. Now, this is a piece of electronics that I have been looking forward to take a closer look at and really just show you some really nice details and what I will call here the extraordinary design effort. But maybe not just design effort, but there has clearly been put some money into using enough components to get what they wanted here. There are no shortcuts or loops. They're just throwing so much gold in here that this just has to be done. That's really nice to see. So let's take a closer look at full resolution. So if we start up here in the left corner with the input connector, the signal we can clearly see from the ground stitching goes over here and through maybe a little preamplifier or a kind of protection, but from the power supply rail design here I would say it's a small preamplifier. From here we can follow the signal going down into a Anoren Singer 1P503 3S, which is a hybrid coupler. That means that the signal coming in on this port is 90 degrees out of phase on one of the output ports. So it's actually phase shifting the signal into two new signals, which are 90 degrees apart. From here it goes into these NXP LDMAS, which is a dual LDMAS, which can output 5 to 15 watt of power, depending on how it's driven. The symmetrical output is then again combined via the same hybrid coupler. We can see that the tracks from the output connectors here go up here, connect, and go out here and connect. So these are even signal paths. So this is just a preamplifier for the larger output transistors that we will see further down. From here on, the signal goes down into a much bigger Anoren Singer 2 hybrid coupler. And here something interesting happens. This also splits the signal out into two new, 90 degrees out of phase. But we have another coupler sitting in between, but this is a direct coupler. Now, a direct coupler does not phase shift the two signals from each other. But if we'll take a look at the output ports, we also see we have 50 ohm termination on the crossing over here. But if we take a look at the output ports, we can see that one port goes directly down to the one side of the dual output MOSFET, while the other one has a bit longer path here. And that means that this is most likely a Dorothy amplifier. And I have taken a much closer look at Dorothy amplifiers and integrated Dorothy amplifiers. So please check out the link in the description or the little info box that you get here on the screen to see more about that. So here we have a 2 times 10 watt output LDMOS. It's an Infineon part. And if we take a look at the output path from this as well, we should also see in a Dorothy amplifier that the output paths are not the same length. So we can see that we have one output here, goes directly down to the large track here, but the other output part actually has a longer path here. And I seem to recall that should be like 1/4 wave length compared between the two to have enough phase shift to combine them again. But what's really getting interesting now that this is just one leg of a symmetrical design. So the output of these two lines are actually combined again in a Anoran Singer 2 hybrid coupler. So they are recombined into the circulator and out to the output. And also, just to repeat myself a bit, the circulator is a magnetic component. It works by that any signal entering port 1 can only get out on port 2 and 3. But as port 3 is terminated to a 50 ohm termination, any signal coming to here will simply just get dissipated as heat. So there can not come any signal from 2 to 1 because any back EMF from the antenna array will get absorbed by the attenuation resistor here on port 3. So this is actually a protection of the output amplifier from the antenna itself. Before moving on to the transmit and receive signal processing parts, I would like to take a look at the back side of the main board, because all the big processors are actually sitting here. These are the processors during the protocol conversion for the DAC and also for the ADC. So we will not see the actual front end let's just call it front end ADC and front end DAC on the signal path on the other side, because they are simply located on the back side of the board, which is, from a point of view of heat dissipation, quite clever that you can have a good heat sink design on this side and you can focus on your signal paths on the other side. Now there's also another connector right here in the middle that is not soldered in, so let's take a closer look at that. So here we can see that's another just spring-loaded connector, just being pressed in. Even the two arms holding it in place is just spring-loaded. That's quite a new thing. I have not seen this done before. Now the main CPU of this unit here is the Altera RRU3928, which is a quite powerful FPGA. As you can see here, it has a whole lot of adaptive logic modules and logic elements that can be programmed, and unfortunately the high ICs here, which are the black ones here and the two silver ones, it's absolutely impossible to find any information on these. These are most likely Chinese made and are not publicly available. It actually says Taiwan. Oh, there you go. Nonetheless, I have not been able to find any data on these ICs. Other than that, here on the back side we can just see a whole lot of ground stitching. Other than that, there's not many components for the other side besides the processors and CPUs. Now over at the power supply, there's a few interesting details. We can see here that there's some gold patterns, which I think is actually heat sinking for the output chokes for the MOSFET stage. And down here we have the that was all the TVS protection, and this is the input choke. And there's a little driver circuitry for the MOSFETs sitting on the back side here. Here at the top we have the transmitting circuitry. Now we can see the back side of the FPGA here, which does the whole protocol to digital digital bit stream conversion that is being fed into the DACs. So let's take a closer look. First we can see all the input resistor arrays here, and the signal line, yeah, we can only guess about that. But the first stage is the analog devices TX DAC, which are dual 16-bit 1230 megasamples per second devices. So these split out to each their channel. And if we go on from here, we have up here a PLL, which is a analog devices ADF 4902, used to clock the sequence down from the ADC. Then we have a analog devices ADL 5372, which is a modulator. We can follow the signal path here, that it's simply just a straight line output here, going right over to the modulator here. Then it gets a little mysterious, because there's a mystery component here. I have not been able to place it. Is it for the receiving part or the transmitting part? Because there is actually a few, you can see holes in the ground stitching, so we could assume that, but also the other way, so it's really hard to tell what this is really doing. But on the output side, before coming to the output connector down to the duplexer, we have a triquint 6-bit 0.5 dB variable gain amplifier. So this is actually just like a turnable knob. You can just turn at 6-bit resolution, and you can adjust how much amplification you want to give to your duplexer. So it's actually using this with some feedback and just adjusting itself to have the right output power, which is necessary at the location. The receiving part is what we have here. Down here in the bottom we have the connector to the receiving part of the duplexer. So let's take a closer look at the signal chain going upwards here. From the input connector we can follow the ground stitching, and we have a lot of Neditech SAW filters sitting around. You can see there's 1, 2, 3, 4, 5, 6 of these placed all around this Skyworks 1.8 GHz RF front end. Unfortunately, I have not been able to locate much more data about that. But from here the signal is again split out into 2 lanes, and up here we have analog devices AD8376, which are dual variable gain amplifiers. And as we can see from the 700 MHz specification of these, that the down conversion mixer must be a part of the RF front end. To learn more about SAW filters and down conversion mixers, there's a link in the description for that. So check that video out where I try to explain these components. So if we move further up here, we have at the last IC before going over to the FPGA located on the other side here, we have a Texas Instrument ATS58C20. This is a dual IF receiver multimode IC for GSM, 3G and LTE. Now it's not really possible to find much information about that either, so we will just have to do with this is the last step of the analog to digital conversion before the FPGA. I am sorry, I completely forgot to show you a really interesting part of the transmitting output board, and that is these AMC 7812. No, these are not 12 volt regulators, but these are monitoring ICs, and quite interesting because just look at what they contain. 16 12-bit ADCs, 12 12-bit DACs, it has 8 general IOs and 2 temperature sensors, one internal and one external. So just imagine the amount of data you can actually collect on something like a output stage of a RF amplifier with some small ICs like this. And it's well integrated into the design. You see it's split up, so there's an IC for each leg of the amplifier. But that is really a nice feature. I have not seen it implemented like this at such a let's say so many measure points before. There has been some smaller monitoring ICs, but we are not anywhere near so many inputs. So it's really interesting to see that these are getting much more monitored, and the possibilities to actually adjust your amplifier based on feedback from what you measure in it during operation, like temperatures, or that you have too much gain in one side, you can adjust it from the signal path input stages to the duplexer and power amplifier. That's really something. So I really hope you enjoyed this circuit analysis, and hope you got enough gold overload, that you saw the kind of pieces and details that you really wanted to take a look at. Also, you can check out the high resolution pictures, which will be on my website. Also, there's a link for that in the description. And if you like my videos, subscribe to the channel, check out some of the other teardown videos. I got a lot of RF videos. So I hope you enjoyed it, and until next time, see ya.